So here we are again. We're twiddling, twiddling with toys, and I'm twiddling with toy magnets here. And what we're doing is observing close-packed cubic, sorta, kinda, because you can make a close-packed cubic if you look at it this way, because they're staggered. Or you can look at it this way, and they're not staggered. You can see right through them. You can sort of. If I had a light on the other side, maybe like this. See, look at that. Not cool, huh? Yeah. Okay, so we can see through them, and this way they're kind of lined up on top of each other. This way they appear to be staggered. And this is what close-packed cubic is. If you're driving by like farm fields, and you know those darn farm fields are planted in straight rows, right? But when you're driving by, they're parallel to your line of travel as a general thing. I mean, not always, but you're going along, even if they're parallel to your line of, like perpendicular to your line of travel. When you get sideways to them, you notice that they line up in kind of different staggered ways. See what I mean? So close-packed cubic and probably regular cubic are kind of the same thing. Just depends on which way you look at it. And I mean, when you want. I was trying out my laser idea for a electron microscope, and I got it focused up on my wall, and I'm holding it in my hand, kind of like my camera is now, and so it was kind of shaky, but I got it to focus, and I could see the carbon atoms inside a diamond, and this is pretty much exactly what they looked like, except they're not so close together. They're not that close together. There's a gap between them, and there's like the little rod and ball, stick and ball diagrams of atoms. That's kind of what they look like, but they're in this cubic array, this absolutely perfect, because carbon atoms, they're all the same size, and so they line up in perfect little rows and columns, and they do so not just in flat surfaces, but in 3 dimensions. And they're as close as they can be. Right? If I start taking these lines that go horizontally across this, they can go forever. And these are just part of that structure, right? This is a space filling tiling of spherical units, okay? And the spherical units are not, in this case, in carbon or AUPT and that sort of thing. They are unit cells. And they're not necessarily just single atoms. They can be, I think the ones in AUPT are 13 atoms. And if you look down this way, you'll see that there's 6 atoms, kind of, 1, 2, 3, 4, 5, 6, around, and one in the middle. And there's one on the other side, and there's this arrangement that has kind of 3. If you look here, 1, 2, 3 more atoms on that side, and 3 more on the other side, and all of a sudden you've got 13 of them, and that's that octagonal arrangement that we find in diamond crystals, and that's why diamond crystals are diamond shaped. And they are diamond shaped. You find them out there on the ground, and they are in fact diamond shaped. Many of them, not all of them, but many. And that's not the only thing that's diamond shaped and 10 on the Mohs scale of hardness. Just because it's diamond shaped and 10 on the Mohs scale of hardness doesn't mean that it's a diamond. It means that it's cubic and some sort of metal that formed deep underground. That's what it means. And they're packed together as closely as they can get, because when they formed, and then they become solid, right? When they formed, everything was under thousands of times more pressure than they are here on the surface. And they retain that closeness together until otherwise, with it takes all that energy to break them apart. And that's one of the reasons why platinum is so hard to melt, because of the density of the material. So, and that's what a platinum unit cell looks like, right? And it could have that many atoms, and I think there's like 256 here or something. 265, I don't know. Endless magnetic fun, whatever it is, and Twiddler Toys didn't tell me how many I got. Free storage bag inside. Oh, far out. I didn't know that. That's far out. Hey. So I don't lose my little balls. Got a sack for my balls. Far out, man. So that's what I'm doing this morning, folks. I'm playing with magnets again. This is like an ongoing theme too. I've been doing this for years and years and years. Albert Einstein used to play with glasses of water with dust in them, right? Because the sun came through and he could see the sun passing through the water, and the little dust motes inside that water, and the water's standing still, right? It's not moving at all. There's no input of energy. But those little dust motes are moving around, bouncing around, and you can see them, right? It's called Brownian motion. Einstein sat and watched and watched and watched, trying to figure it out. How come they're jiggling? This is what Richard Feynman called it. When nobody's jiggling them. How does that happen? And you know, Einstein told us that God does not play dice with the universe. Here's a dice. Where's this dice? Yeah. And he was right. He was right by default, kind of the other way around. You know, the dice part is a big part of our universe, and there really isn't any such thing as magic. No invisible guys in the sky, you guys. There's guys in the sky, but they look like us, and they're pretty much. That's why you can't find any aliens, 'cause there aren't any. Them are us. And I've been thinking about that for a while now. Didn't have anything else to do but think. Peace, y'all. Peace. Imagine world peace. That's all we have to do.